Hello friends, in this session we will see standard second order system time response analysis. We will also see the impulse response characteristics of a second order system. Let us begin. So let us try to understand how a standard second order system looks like. Okay, let us see that first. So definitely we will be having some block here, correct? Just as we had seen for the first order system, and here inside this we will be having omega n squared upon we will have s into s plus 2 zeta omega n, correct? And definitely here we are going to have this output c of s, and definitely we are going to have some input r of s. But now as we have seen that it is going to be a closed loop system, so definitely this is going to be like this. So this is going to be a unity feedback closed loop system this way. Is that correct? Definitely here it is going to be minus sign, and this is going to be E of S. Is that correct? Yes. Now we have seen that whatever this particular open loop transfer function that we have here, I mean to say this omega n squared upon s into s plus 2 zeta omega n, this thing is called as loop gain. Is that correct? We have seen that already. So we can say that this omega n squared upon s into s plus 2 zeta omega n is nothing but what? It is nothing but loop gain. This is nothing but loop gain, correct? Yes. Now you please tell me what is the type of the system and what is order of the system. If you just observe that this particular loop gain has only one pole at origin. If you check out, it is having only one pole at origin. This loop gain is having only one pole at origin. This means what? It is going to be a type 1 system. What about order, sir? What about order? Yes, this name itself suggests that it is going to be second order system. So it is going to be type 1 order 2 system. Is that correct? Yes. Now we will try to understand what are these different things inside this. Means what do we mean by this omega n? What do we mean by this zeta? So let me start with the first one. What is omega n? Omega n is nothing but natural frequency of oscillations. It is referred to as natural frequency of oscillations, correct? Yes. Now what is zeta, sir? Zeta is nothing but called as damping ratio. Zeta is called as damping ratio. Okay. Now basically what happens is, whenever we speak about second order system sort of, then we can have the poles to be complex conjugate or not. Poles can be complex conjugate, correct? Yes. So if the poles are going to be complex conjugate poles, right, then what will happen if we find their inverse Laplace transform? Then we would understand that they will be having some response which will be having some oscillations like this. We will talk about them in detail afterwards as well. Okay, just for time being, in order to understand you. So the frequency of these oscillations is nothing but our natural frequency of oscillation, which is omega n, correct? And this zeta is nothing but called as damping ratio. Means if these oscillations which are there, if they die down at the end at infinity, correct? So that particular information which is there, means for example oscillations are going to be there like this, correct? And after some time if they die down to zero, means if you observe here, if you see, you are having no oscillations. Is that correct? So what will happen now? What will happen now is, in such a case, if you see, this information that my oscillations are damped will be given by this damping ratio. Is that correct? Now let us see what is overall transfer function for the system. Means whatever we have seen till now is the loop gain, correct? About this loop gain, but what is the overall transfer function of this system? what is that going to be? If you see, this is going to be C of s upon R of s, correct? So, and if you observe, it is always equal to what? G upon 1 plus GH. Is that correct? Yes. And here if you see, H is going to be 1. Why? Because it is unity feedback already given here. Unity feedback system. Correct. Which means now your C of s upon R of s, if you calculate, you will get C by R to be equal to omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. If you, and this you have got from the equation, that is g upon 1 plus gh, wherein you have to substitute h equal to 1, and whatever is g. G is what? G is nothing but a loop gain only, omega n squared upon s into s plus 2 zeta omega n. Is that correct? Yes. Now, if you check out, this is going to be overall transfer function. Correct? Now, you please tell me, if it is overall transfer function, then denominator of this overall transfer function will give you what? It will give you the characteristic equation, correct? So denominator of the overall transfer function gives you characteristic equation, which is nothing but what? S squared plus 2 zeta omega ns plus omega n squared. Is that correct? This is going to be your characteristic equation. Now, we need to understand one thing. Now, we have to do the time response analysis on this. Now, before entering into our analysis, we will try to see what are the parameters which have to be varied. So if you check out here, if you see, you have basically got only two parameters, means either you can vary omega n or you can vary zeta, correct? But now if you see, what will happen is, I'll tell you, what does this omega n tell you about? Omega n tells you about the, what do we say, natural frequency of oscillations, right? Which means the speed of oscillations. Now if you check out, with respect to our stability or with respect to responses, we are not so much interested into the speed of oscillations. We are definitely interested into the oscillations, but we are not interested into the speed of oscillation. That is the reason there is no point in varying omega n. So cancelled out. What about zeta, sir? Yes, variation of zeta will be exciting to us, because zeta is either 0, because zeta which is there, either it is going to be 0, or it is going to lie between 0 and 1, or it is going to be greater than 1. So now we will have three different cases. We will have different cases of zeta, wherein zeta is equal to 0, zeta is between 0 and 1, and when zeta is going to be greater than 1. Those are the some cases. We will try to see them, and for those cases we will try to find what is called as unit impulse response UIR and unit step response USR. We will try to find them, correct? Now let us try to start with the UIR, unit impulse response of a second order system. Let us see that. Yes. Now the moment I say that it is going to be unit impulse response, it means what? The input to the system is going to be what? Definitely del of t. Is that correct? Yes. Now also we will be analyzing the system for all the four cases in the sense, whenever zeta is equal to 0, zeta is between 0 to 1, and when zeta is going to be greater than 1, and when zeta is equal to 1, correct? Those will be the four cases. What are the four cases? When zeta is going to be 0, zeta lies between 0 and 1, zeta is greater than 1, and when zeta is equal to 1. Those are the four cases. We will try to see what happens inside the system whenever my zeta is 0, or it is between this 0 and 1, or when it is greater than 1, or when it is equal to 1. That is what is our intention. So the first case we will try to see what it is. So let me have the first case. Case 1. Let me call case 1 to be equal to zeta equal to 0. What happens? You please tell me, when I say that my damping factor is 0, when I say that zeta equal to 0, it means what? My damping ratio is 0 or not? Yes. So if my damping ratio is 0, which means what? There is no damping. If my damping ratio is 0, it simply means that there is no damping. And if there is no damping, then it implies that the system is going to be undamped system. Getting my point? It is going to be undamped system. Now, what is overall transfer function? Overall transfer function we have already seen, right? Let me call it as g of s. This is overall transfer function. It is not the loop gain. Please mind. It is omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. Correct? This is our overall transfer function. Now, when I'm saying case 1, when zeta equal to 0, what do I mean? I mean that just replace zeta by 0. If I replace zeta by 0, zeta equal to 0, what is going to happen here? It is going to be omega n squared upon s squared plus this 2 into 0 plus omega n squared. So this is going to be omega n squared upon s squared plus omega n squared. Is that correct or not? Yes, it is going to be correct. This is your g of s. So this is basically your impulse response, but this impulse response is in Laplace domain. You want it in time domain. So if you want it in time domain, which means you will be immediately applying what? Inverse Laplace transform for the same. So if you check out inverse Laplace transform for this one, you will get something to be, so Laplace inverse of g of s to be equal to Laplace inverse of omega n squared upon s squared plus omega n squared. Correct? So it is going to be equal to, if you check out what happens now, Laplace inverse of omega n squared upon s squared plus omega n squared. If I bring one omega n out from this numerator, I will get omega n into Laplace inverse of omega n upon s squared plus omega n squared. Is that correct? If you see, it is going to resemble to something called as sine omega t or not? Yes. So if you see, this is nothing but equal to this Laplace inverse of omega n upon s squared plus omega n squared is nothing but equal to sine of omega n t. Is that correct? Sine of omega n into t. So what is your response? Your response y of t which is there, your response y of t which is there in time domain is going to be, your impulse response is going to be this one. So this is going to be your unit impulse response when your zeta is equal to 0. Correct? Now, if you check out, is there any transient term? No. First of all, what do we mean by transient term, sir? Transient terms in the sense, transient term means that a term which will become 0 when t tends to infinity. If you check out, is there any term in this particular expression of y of t for which my expression y of t will become 0? No, right? There is no term for which, there is no term in this expression of y of t which will become 0 when my t tends to infinity. Is there so? No, nothing, which means that there are all steady state terms. So how does the graph look for this one? Let us see. Is it same as, like, a sin t? For example, if you see, is it similar to this one? Yes. How does the plot look for this one? The plot is going to be like this, right? It is going to be a sine wave. So, and this particular amplitude which is there, here it is going to be a. So if you compare, here it is going to be omega n. So here it is going to be omega n minus omega n, and this is going to be y of t with respect to t definitely, and it will go on up to infinity. Is that right or wrong? Now you please tell me, is it so? This is definitely, this maximum value is always going to be plus omega n on the positive side, and on the negative side it is always going to be equal to what? Minus omega n. Is that correct or not? Yes. Now if you check out, for the impulse input, the response has sustained oscillations. If you see, these oscillations which are there, they are sustained oscillations up to infinity. Means oscillations will be there, but they will be sustained oscillations. Means oscillations do not die out. So sustained oscillations. Is that correct? Sustained oscillation, which means what? Does not die out. Does not die out when t tends to infinity. Correct? Moral of the story is what? The unit impulse response of a standard second order system in undamped condition, because we seen that this is for zeta equal to 0, correct? This is when zeta is equal to 0, which means it is going to be for undamped condition, we have seen. So if it is for undamped thing condition, right, then it will be having sustained localized oscillations with frequency of omega n. What is the frequency now here? What will be the frequency? If you see, if this is sine omega nt, so definitely frequency is going to be omega n. So it is going to have sustained oscillations of frequency omega n. Frequency is going to be omega n, correct? And hence it, now you please tell me, is it stable or unstable? Since it is having localized oscillations, we have seen that whenever your system oscillates, then it is definitely not a stable system, correct? Yes, so it is not a stable response, correct? Yes. Now let us try to see for zeta lying between 0 and 1. Let us see what happens there. Now whenever zeta is between 0 and 1, it implies what? It implies something. It implies that the system is definitely damped. Why? Because your zeta is having some or the other value, correct? Which means it is definitely damped. So this is going to be a damped system. But in damped also we will have some types. Like whenever zeta is between 0 and 1, we call it to be under damped system. We say that system is going to be under damped system. So whenever zeta is between 0 to 1, we call it as under damped system. Now next, what happens next? Let us see g of s. What is g of s? G of s, what was there? What we had discussed earlier? Omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. Is that correct? Yes. Now since zeta is between 0 and 1, we cannot put it either 0 or 1. If you check out here, what has happened is zeta lies between 0 and 1, correct? Which means we cannot put it to be equal to either 0 or 1, correct? See, it is a simple thing. If you put zeta to be equal to 0, then it becomes undamped system. If you put zeta equal to 1, then we will see that later. But for time being, if you see, is there any equal to sign there? No, which means the zeta which is there, it is purely lying between 0 and 1. Is that correct or not? Yes, it is correct, sir. So we need to use this complete quadratic equation. Now to get this impulse response, we will have to get the inverse Laplace transform of this particular g of s. So let us try to find the inverse Laplace transform of our g of s, correct? Now in order to factorize, let us try to factorize our denominator, correct? So now if you see, because we have seen that in order to get inverse Laplace transform, in order to get inverse Laplace transform, you should have those particular poles down, correct, on the denominator, and those poles which are there, those poles have to be in factorized form. So how do you find those factors, or how do you find those poles? So in order to find those second order poles, what we can use is something called as formula method. Formula method, which we had studied in our school days, correct? What does it say? For example, if you see, what equation we used to have in school, we used to have something called as ax squared plus bx plus c equal to 0. Is that right or wrong? Yes. So definitely, so similarly here you have some equation like this. If you compare, what do you get here? You get that your a is equal to 1, your b is equal to, see, this is with x, correct? So with s, whatever term you have, so it is going to be 2 zeta omega n, 2 zeta omega n, correct? And then c term is what? C term is going to be omega n squared. So c is going to be omega n squared. Is that correct or not? Yes. Now what happens next? What happens next? What will be there? So this particular formula method, it says that your poles which are there, poles or your roots, or basically poles which are there, those will be nothing but minus b plus or minus under root of b squared minus 4ac upon 2a. Is that right? Yes. So if you just substitute that here, what do you get? Let us see. If you substitute that here, what do you get? You get s1 comma s2. Let this be the poles. What is there? Minus b. So it is going to be minus b. What is b? B is going to be 2 zeta omega n. So it is going to be 2 zeta omega n. then you are definitely having plus minus sign, so it is going to be plus minus. Under root of what? Definitely it is b squared minus 4ac. So what is b? B is nothing but again 2 zeta omega n. So definitely 2 zeta omega n the whole squared. If you do, then you get 2 squared is 4 zeta squared omega n squared. Correct? Minus what do you get then? Minus what do you get then? Yes, 4 AC. So it is going to be 4 AC. A is how much? A is going to be 1. And what is C? Omega n squared. So 4 into 1 into omega n squared. So it is nothing but 4 omega n squared. Is that correct? Yes. Now divided by what? What is that? You have got 2A. So 2 is going to be 2 only. What is A, sir? A is going to be 1. We have already seen. So it is going to be 2 only. Correct? Now, if I further simplify, let me just take this 4 zeta, or rather 4 and this omega n out. Let us see what happens. Correct? What will I do is, let me tell you. I had s1 comma s2 to be equal to how much, sir? I had it to be equal to minus 2 zeta omega n plus minus under root of 4 into zeta squared omega n squared minus 4 omega n squared. Correct? This is what I had, divided by 2. This is what was the equation. Is that correct? Yes, sir. Now what will I do is, let me just write this whole thing 2 zeta omega n plus minus. Now what will I do is, here see, this is under root. Correct? What will I do? Let me take this 4 and omega n squared common. So if I take that 4 and omega n squared common, inside the bracket what do I remain? It becomes zeta squared minus 1 is remaining. Is that right or no? Yes. And definitely divided by 2 will be there. So yes, what do you get now? It is going to be equal to minus 2 zeta omega n plus minus is going to be there. Under root of 4 omega n squared is how much, sir? Under root of 4 omega n squared is nothing but 2 into omega n. Correct? Under root of what is there? Definitely zeta squared minus 1 remains under root. Now the whole divided by 2 is what we have. What happens now? If we divide by 2, definitely these 2 and these 2 will get cancelled along with this 2. Correct? So you will be having minus zeta omega n plus or minus omega n into under root of zeta squared minus 1. Correct? Zeta squared minus 1. Is that right? Yes. Now here comes the catch. Here comes the catch. What happens here is, see, whenever your zeta lies between 0 and 1, which means definitely it is going to be less than 0 or not? Yes. So if zeta is less than 1, so because whenever I say that zeta lies between 0 and 1, it means that zeta is going to be less than 1 or not? Yes. If zeta is going to be less than 1, then the square of that less than 1, for example, let me take that to be equal to 0.5, for example, then it is going to be 0.5 squared. Is that right? And if it is going to be 0.5 squared, because here I am having zeta squared, right? So if it is going to be 0.5 square, then it is going to be 0.25. Correct? So if you see now again 0.25 minus 1 under root, that is what we have here. Correct? What happens then? Whatever term you get, that is going to be negative of 0.75. Correct or not? It is going to be a negative term. So in order to think of that, what we will do is, we will do one simple operation. What we will do, inside whatever is written, we can just flip this what is written here, and we can just add j outside. That is what we can do. Just flip this and we can add j outside. If you do so, what do we get? Let us see. So s1 comma s2 will be equal to, if you check out, minus zeta omega n is going to be same, plus minus is going to be same. Just what did I say? Just add this j and flip the internal things. So if I add j into omega n into under root of, initially it was zeta squared minus 1, now I will have 1 minus zeta squared. That's it. Is that right? Yes. Now what I'm saying is, if you observe this term, this omega n into under root of 1 minus zeta square, this is imaginary term or not? Yes. So this imaginary term which is there, no, we call it to be equal to, what do we say? Damped frequency of oscillations. Damped frequency of oscillations, and it is given by something called as omega d. So if we check out, now we have got one more new term which is called as omega d, and it is equal to omega n into under root of 1 minus zeta squared. This is what we have got. We have got this one more term now. So If I just replace this whole thing by omega d, then what do I get? I get s1 comma s2 to be what? Minus zeta omega n, correct? Plus or minus the j comes as it is into omega d, because this whole thing will be replaced by omega d. Is that correct? Now you may ask me, sir, why you can say that it is going to be frequency of oscillations only, damped frequency of oscillations only? Because if you see now this zeta which is there, zeta is the ratio, right? We have seen that it is a ratio. If it is a ratio, then definitely it is going to be dimensionless or not, because it is going to be dimensionless. So if it is going to be dimensionless, then what will happen? Whatever thing it gets multiplied with will, I means if it is going to be, for example, in our case when it is omega n into under root of 1 minus zeta squared, if this zeta square is going to be dimensionless, then definitely this whole term will be what? Dimensionless or not? Yes. And if it is multiplied with this omega n, and omega n is what? Having radians per second. Unit is this one, radians per second. So definitely for omega d also, our, what do we say, is going to be radians per second only. So it is going to be again frequency of oscillations. That is what I have to prove, correct? And yes, definitely it is multiplied with this under root of 1 minus zeta squared, and this zeta is associated with damping. Hence we say that it is going to be damping frequency of, or damped frequency of oscillations omega d. Is that correct? Yes. Now what can I do is, see, if these are the two roots, right, then yes, definitely we can rewrite our, so these are the two roots, so we can definitely rewrite our transfer function as g of s is equal to omega n squared, correct? It was what? 2 zeta omega ns plus omega n squared, correct? This is what it was. We can definitely rewrite it as omega n squared upon, what do we say, s squared plus 2 zeta omega ns plus omega n squared, correct? So this one we have already splitted it into these two factors. We know that the two factors which are there are this one. So definitely I can write that one as s plus zeta omega n plus j omega d into s plus zeta omega n minus j omega d. Is that correct or not? Yes. Now you can use two methods to solve this. What are the two methods? Either you can use partial fraction, your traditional method, partial fraction method, or I have one more method which is a new method which we will use now, and it is going to be very easy method, new method, in order to solve this. How do we do that? Let us see. Let me just write down what we have. See, we have this g of s to be equal to this one. Let me just rewrite it over here one more time. Yes. Now let me use this new method. What does it say? Let us see. If you observe this one and this one, means s plus zeta omega n, are they same or not? Let me call them to be a. Now if you see this j omega d and this j omega d, are they same or not? So definitely this is b. If you see between them, here we have got this plus sign, between them here we have got this minus sign. So and it is going to be multiplication of this both. Is that correct or not? Yes. Now if you observe, is it a plus b into a minus b? Yes. So if it is a plus b into a minus b, then definitely what is the answer for this one? It is going to be a squared minus b squared. Is that right or wrong? Yes, it is right. We have seen that in school, correct? Yes. Now by using the same relation, what do we have is, let us see, by using the same relation, g of s to be equal to, what do we get? Omega n squared upon, definitely we can write a squared minus b squared. So what is a squared? A is what? S plus zeta omega n. So I can write s plus zeta omega n the whole squared minus b squared. What is b? J omega d. So it is going to be j omega d the whole squared. Is that right? Yes. Now which is equal to what, sir? Which is equal to omega n squared upon, what happens? S plus zeta, that will be same, s plus zeta omega n the whole squared minus, what do we have? J squared into omega d square. If you just separate this, squares, so You get it to be j squared into omega d, and we know that j square is equal to what? J squared is equal to -1, so this -1 will get multiplied with this minus, so you will get definitely plus sign. So this is going to be plus omega d squared. Is that correct? Yes. Now let me write this down on the another page so that it becomes easy for us. So what do we have now? G of s to be equal to omega n squared upon s plus zeta omega n the whole squared plus omega d square. This is what we have seen now, correct? Yes. Now what I'm saying is, what if I take, or rather, what if I multiply and divide by omega d? What happens? Let us see. If I multiply and divide by omega d, let me just multiply by omega d and divide the whole thing by omega t. Correct? Let me just do that. If I do that, what do I get then? Let me just take this omega n squared and this omega d outside. So omega n squared upon this omega d outside, and inside let me have this omega d upon this whole term. So let me have inside omega d upon this whole term. So it is going to be s plus zeta omega n the whole squared plus omega d squared. Is that correct? Yes. Now let us see what happens. Now what do we have? Let us try to apply inverse Laplace transform now. Let us apply inverse Laplace transform. Why I did this step, you will understand it very soon. See, let me apply inverse Laplace transform. What happens? You will get this y of t, correct? Which is nothing but what? Yes, definitely Laplace inverse of what? Laplace inverse of what? Yes, it is going to be omega n squared upon omega d, this thing multiplied by omega d upon s plus zeta omega n the whole squared plus omega d squared. Is it same as sin 80? Yes, it is going to be same as sin 80. But what do we get here? See, omega n squared upon omega d. Will it be there or not? Yes, omega n squared upon omega d will be there as it is. They will come out. What about this Laplace inverse? Laplace inverse of this is going to be what? Yes, definitely it is going to be, what do we say? Sin omega dt, correct? It is going to be sin omega dt, omega d into t. But if you see, it is shifted here in frequency s plus zeta omega n. So definitely here we will be having e to the power, since it is plus here in frequency, so definitely we will be having in time minus, so minus zeta omega n into t. Is that correct? Yes, this is our expression. Now let me just split this omega d as well. Let me just put this omega t to be whatever it is, so omega n into under root of 1 minus zeta square, that is what it is, correct? So let me just replace that and see what do I get. So finally y of t that you get is going to be, see, omega n squared is there already, omega n squared upon omega n into under root of 1 minus zeta squared into e to the power minus zeta omega n t into sin omega dt. Is that correct? Yes. Now let me just cancel this omega 1 omega here and 1 omega n here. It is gone. So what do we have at last? What is the final expression? At last the final expression is going to be omega n upon, what do we have? Under root of 1 minus zeta squared into what? E to the power minus zeta omega n into t into sin of omega d into t. Correct? Is that right or wrong? Yes. Now what do you observe? What happens if I put t equal to infinity here? Means what happens to this expression when I put t equal to infinity? If you see, when I put t equal to infinity, then definitely this term, when I put this t to be infinity, then this becomes e to the power minus infinity, and if it becomes e to the power minus infinity, then definitely e to the power minus infinity is going to be 0, which means at t tending to infinity it is going to become 0, which means this is definitely having only transient terms. It is having only transient terms, correct? Now how will the plot look like, sir? Yes, definitely. See, since it is going to be sin omega dt, so definitely it will be there, so sin omega dt will be there. But at the same time, what is going to happen? It is going to decay in this way. So let me draw this decay first. So it is e to the power minus zeta omega n t. So this is going to be the decay. This is going to be the decay. And within this decay, I will be having my sine wave. This is how it will go. And finally, it is going to become 0 at infinity. T. Correct? This is going to be your y of t. Is that correct? Yes. Now, from this graph, what do we understand? We understand that whenever my zeta lies between 0 and 1, then for an impulse input, the response has damped oscillations. Because see, oscillations are, damped. These are called as damped oscillations because at the end they are becoming 0. So it is called as damped oscillations, which eventually die out for underdamped system. That is what we get. That is the response. Correct? So we can say that the unit impulse response of a standard second order system in underdamped case will have damped localized oscillations with a frequency of omega d, and it indicates a stable system. It indicates stable system, correct? Because it is going to die out at the end. The oscillations which are there, they will die out at the end. That is the reason we can call it to be stable system. Now let us see the third case. What is the third case now? Third case is just nothing but zeta equal to 1. Now, what does it happen? See, whenever we say that zeta equal to 1, this implies that the system is going to be critically damped. Always remember that. Definitely it is going to be damped because damping ratio is non-zero. But at the same time, whenever we say that zeta is equal to 1, then it becomes critically damped. Is that correct? Yes. Now, let us see our thing. What happens? What was our transfer function, overall transfer function g of s? What was that? It was nothing but omega n squared upon s squared plus 2 zeta omega n s plus omega n squared, correct? Now, what happens if I put zeta equal to 1? What happens now? Just put that, you get g of s to be equal to what? Omega n squared upon s squared plus, what happens is 2. Zeta is going to be 1, so zeta equal to 1. 2 omega ns plus omega n squared. Is that correct? Yes. Now if you see, this is nothing but a quadratic equation which can be also written as omega n squared upon. What is that? It is just a simple quadratic equation. It is the equation for s plus omega n the whole squared. Is that correct? Yes, s plus omega n the whole squared. That is what it is. So this is our g of s. Is that correct or not? Yes. Now, what is our next task? Next task is going to be to find the inverse Laplace transform. Let us try to do that. So, how do you do that? Definitely your g of s is nothing but this omega n squared upon s plus omega n the whole squared. How does that look now? See, inverse Laplace transform of this. How does that look? Yes, if you just check out, it is like omega n upon s plus a, sort of, correct? So this one, if you see inverse Laplace transform from your mathematics point of view, you must have learned if I take omega n squared here, like sort of Laplace inverse of omega n squared upon s plus omega n squared, correct? That is what is there. Now, if you take this omega n squared out, what do you have inside? You are going to have 1 upon s plus omega n squared. Sort of, if you just ignore this omega n, what do you have? Then you will be having 1 upon s squared. So 1 upon s squared nothing but gives you t. But at the same time, it is going to be frequency shifted or not by plus omega n. So definitely it is going to be a to the power minus omega n t will be there. Is that correct? So this is nothing but your y of t. This is nothing but your final expression for a critically damped system whenever zeta is equal to 1. What is your impulse response? So it is your impulse response. How does that look on the graph? How does the plot look? Plot looks something like this. The plot looks something like this. It just increases because see, since it is having this t component, then it is going to increase, and finally, since it is having e to the power minus omega n t, so whenever my t tends to infinity, it is going to become 0 finally. So definitely, its graph is going to be somehow like this. This is its graph. That's it. Solved. Problem solved. This is 0. This is going to be y of t. Correct? This is the graph. Now, what do you infer from this graph? You infer that whenever t tends to infinity, my response which is there, it will become 0. Now, you please tell me whether there are transient terms or steady state terms? Definitely there are only transient terms. Why? Because at t tending to 0, this term which is there, it is going to become 0. Correct? So it is going to only have transient term. Correct? Now what happens next? What happened here? See what happened now. Impulse response, we know that it is expected to be 0 when your t tends to infinity. Correct? So when you say that the unit impulse response of a standard second order system in a critically damped case, because this is critically damped, in a critically damped case, unit impulse response of a standard second order system will be always stable. Will be always stable. Is that correct? Now, if you check out one observation, what is that observation? Oscillations came only when we had complex conjugate poles or not. Yes. When we don't have complex conjugate poles, we don't have oscillations. Correct? This is just a thing which we have observed. Observations are definitely much necessary. Correct? Now, let us think of case 4, final case. When zeta greater than 1, whenever we say that zeta greater than 1, it implies something. It implies that the system is going to be over damped system. Getting my point? It is going to be over damped system. Definitely it is going to be damped. But if you see the zeta value, whenever zeta value is greater than 1, we say that it is going to be over damped system. Why we say that? So we will see that very soon. Okay. Now, definitely, what is our g of s for a overall transformation for a standard second order system? Definitely it is going to be omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. Our same old story, correct? Same old story is going to be repeating. Now, what happens here? So by using the formula method of finding roots of quadratic equation, definitely, because since it is greater than 1, we just don't know the exact value, so we just cannot replace that here. Correct? Yes, that is the reason we will be using the full equation. So by using formula method, which we had studied in school, what do you get? You get s1 comma s2 to be equal to, definitely yes, the same old story which we had got, 2 zeta omega n plus minus under root of 4 zeta squared omega n squared minus 4 omega n squared. The same old story is going to repeat. Nothing will change. And at the end we had got this to be, minus zeta omega n plus minus omega n into under root of zeta squared minus 1. That is what we had at the end, correct? Same expression we had got. If you check out this one, where is that? Yes, see, here we have got the same expression. The same expression we have got here also. Correct? Here also. We got the same expression. Now note that what is going to happen. See, first thing is these are our poles. Second thing is just observe. Many people will tend to make a mistake. They will say that this is omega d. But it is wrong, it is not omega d, because omega d is what? It is nothing but omega n into under root of 1 minus zeta square. It is not zeta squared minus 1. Please make a note of this. This is going to be very important. So now once you have these poles, we can definitely substitute them, in this equation sort of. So what do we have? We have g of s to be equal to what we had, omega n squared upon s squared plus 2 zeta omega ns plus omega n squared. Correct? So the same thing which is there, that can be represented in the form of factors. In the form of factors, in the sense, definitely omega n squared upon, what do we say, s plus zeta omega n plus omega n into under root of zeta squared minus 1. Correct? Zeta squared minus 1 multiplied by s plus zeta omega n minus omega n into under root of zeta squared minus 1. Correct? This is what we had. Now, same old story repeating. This we call it as A, this we call it as B, this we call it as A, this we call it as B. Same old story. If you see, it is again going to be what? A plus B into A minus B. Same as A plus B into A minus B, if you see. Minus B, A plus B. Correct? Same old story. This is nothing but what? A square minus B square. So we are going to do the same thing. So what do we get here? We get After solving, you get g of s, which is there. You get omega n squared upon a squared minus b squared. What is a? S plus zeta omega n. So you get s plus zeta omega n the whole square. This is going to be a square minus, what do you have? You have b square. So what is b? What is b? B is going to be what? Omega n into under root of zeta squared minus 1. Correct? Squared. The whole squared. Is it correct or not? Yes. So this is your this one. Now here comes the thing. Now the inverse Laplace transform of this will involve sine hyperbolic functions. Why? Because if you see, it is like sort of, this is omega n square, forget about it. This is going to be s sort of minus. So because of this minus sign, if you see, you will be getting hyperbolic functions or not? Yes, you will be getting hyperbolic function. Like sort of sine hyperbolic theta and all sort of terms you will be getting, because we know that Laplace transform of sine hyperbolic kt is nothing but k upon s squared minus k squared. So this minus sign, this minus sign is what is the problem. So it is going to give you hyperbolic functions, and it is not at all important to us to analyze in control systems. We don't want to analyze hyperbolic functions here in our subject, control system. That is the reason what we have is, we have brought a concept of dominant pole. That is the reason we have brought a concept of dominant pole. What is that concept? We will see that very soon, just now, immediately. Now, before using this particular concept of dominant pole, let us first try to plot the poles on the S plane. What we have got, let us try to plot the poles. So what are those poles? Poles are definitely this one, what we have, correct? S plus zeta omega squared, where are they? Yes, these are the poles which we have. Let us try to plot them first. So yes, S1 let it be equal to minus zeta omega n plus omega n into under root of zeta squared minus 1, and let me have another pole which is S2. Let me have that minus zeta omega n minus omega n into under root of zeta squared minus 1. Let us have that, correct? Now what happens, let us see. Do you agree that these particular poles are real poles? Yes. What happens is, I will tell you. Let me try to plot the poles on our j omega axis, on our S plane, basically, not j omega axis, on our S plane. Let's try to plot the poles. See, what happens is, see here you have got negative term minus zeta omega n, correct? And here you have got this plus term, and here you have got this something, correct? For example, if this minus zeta omega n is, let us equal to minus 3, because minus n we have, correct? So for assumption purpose, let that be equal to that way, minus 3. So minus 3 plus something, that will be, for example, somewhere here, minus 2, let us say here you have got the pole. Whereas the same minus 3 if you have here, and you have got more minus term into it, which means definitely it is going to be increased or not? Yes. So if here, if it is at minus 2, so definitely here it will be somewhere at minus 4. Is that correct or not? Yes. So this was our S1, which was equal to how much? Definitely this, whatever the equation it had, it had just minus zeta omega n plus omega n into under root of zeta squared minus 1. First equation, this one. Let me just erase this too. It is not of our any use. It was just an assumption. And our second term is this much. This particular pole, what is that? It is going to be this one. So it is minus zeta omega n minus omega n into under root of zeta squared minus 1. Now I will have to tell you one thing. See, this pole is close to imaginary axis. Yes. This pole is far from imaginary axis or not? Yes. Now what happens is, what does the dominant pole concept tells us? It says that dominant pole is the pole which is closest to the imaginary axis. So if it is closest to the imaginary axis, then out of this S1 and S2, definitely, by the way, this is S2, correct? Now between this S1 and S2, definitely this S1 which is there, it is going to be close to imaginary axis rather, correct? So we call this pole to be equal to dominant pole. So this is our dominant pole. Now what is significance of this dominant pole here? Yes, let us see that significance. Let us see. First of all, the pole which is closest to the j omega axis will be the dominant, because it is the pole which will be closer to instability, because we know that as our pole travel to the right half of S plane, it becomes unstable. So this is the pole. The first thing is, this is the pole, this S1, it is the pole, it is dominant pole. Why? Because it is the pole which is very very close to instability. So it's going to be close to instability. That is the first thing. Now, what is the second thing, sir? Second thing is, yes, definitely. So, and we are interested in analyzing the behavior of such systems only, which are just about to be unstable, sort of. Correct? Now, whereas the pole which is far away means this one, S2. Let me take another color. And the pole which is far away, this S2, which is there. Correct? The pole which is far away from the j omega axis in the left half of S plane is more stable, and it will not at all affect in your system stability things, performance characteristics. Correct? That is the reason we are not at all interested in analyzing this S2. We are completely interested in analyzing the dominant pole which is close to instability. That is the only thing. That is the only simple reason which I would like to tell you. So we can definitely ignore this S2, correct or not? Yes. So by ignoring this non-dominant pole, this is called as non-dominant pole. Non-dominant pole. And we are going to ignore this non-dominant pole. Why? You have understood that. Why? Because it is going to be stable and it does not affect your system parameters. That's correct. Yes. Now we will only and only consider this dominant pole. Correct. So let us consider that dominant pole. So our g of s, which is there, squared upon, it will only have the dominant pole. So s plus zeta omega n minus omega n into under root of zeta squared minus 1. This is what it will have. That's it. It is not going to have anything else. Correct? Correct? Yes. Now, yes, student may have doubt, sir, but here you have got this minus sign. Array, see, this is minus zeta omega n plus omega n into under root of zeta square minus 1. So when this one goes there, what will happen? Goes on the left hand side, then what will happen? This minus 2 zeta omega n will become plus 2 zeta omega n, and this plus omega n into under root of zeta square minus 1 will become minus omega n into under root of zeta square minus 1. That is the whole thing which we have written, correct? Now, by taking inverse Laplace transform, let us take what happens. Now, if you take inverse Laplace transform, what happens now? Yes, definitely. What will happen? Simply, if you take this, what do we say? Omega n squared as common. For example, this is nothing but Laplace inverse of omega n squared upon s plus zeta omega n minus omega n into under root of zeta squared minus 1. Minus 1. Correct? This is what is there. So, how do you find it? Let us take this omega n squared out. So, it becomes omega n squared y of t. Omega n squared it becomes under, inside that, what do we have? What do we have inside that? Definitely you will be having Laplace inverse of what? 1 upon s plus zeta omega n minus omega n into under root of zeta squared minus 1. Correct? This is what we will have. So what do we have next? Omega n squared into Laplace inverse of. Now this is s plus zeta omega n minus omega n. If you see, it is going to be frequency shift or not? Yes, it is going to be frequency shift only. So if it is going to be frequency shift, then it is definitely going to be how much? Omega n into e to the power what? Because frequency shifted by this plus zeta omega n minus omega n square. Correct? So you will be having minus zeta omega n minus omega n under root of zeta squared minus 1 into t. So this is what is your y of t at the end. This is what is the y of t. Correct? Now, how will this plot look? Let me rewrite the equation. Y of t, which is there, it became omega n squared e to the power minus zeta omega n minus omega n into under root of zeta squared minus 1 into t. Correct? This is the whole equation which we have. Correct? Now, the graph will look how much? Definitely, this is omega n squared. So, at t equal to 0, this e to the power minus 0, which is e to the power 0. So, it becomes omega n squared into 1. So omega n squared is going to be what happens at t equal to 0. What happens when t tends to infinity? Definitely when t tends to infinity, it becomes e to the power minus infinity and it will be 0. So when t tends to it is going to be 0. So definitely this is going to be somehow like this. It is going to be a curve wave like this. Is that right? Yes. Now from this graph we infer that for an impulse input the response is tending to 0 at t tends to infinity or not. Yes, because t tending to infinity, so it is going to tend to 0, and this is what is expected, so it is going to be a stable system. So at the end we can say that the unit impulse response for a second order system which is operated in over damped condition is always stable. Standard second order system operated the unit impulse response UIR. Is that right? Yes. So this particular topic ends the what is the response for unit impulse response of a standard second order system. This is what it ends. Thank you.